This example is for the calculation of a mass spectrometer. Let's say you have a beam of particles, and these are hydrogen atoms, approximate masses of 1.67 times 10 to the minus 27. And that's going to be for this particle here. That would be regular protium, or just one proton in there. And then the approximate mass of hydrogen with one neutron, 3.34 times 10 to the minus 27 kilograms. Okay, and that's deuterium. Now this beam of particles is traveling at 1.00 times 10 to the 6 meters per second, and that's going towards a magnetic field. And these were going to be positively charged particles. Okay, their electrons are not on them. So when they encounter this magnetic field, their path is going to curve. Let's see why. So let's use the right-hand rule. We are encountering the magnetic field in this direction. So point your fingers in this direction. Now wrap them into the board or into the page. And this will tell you that the magnetic field is going upwards, or the magnetic force is going upwards. So what's going to happen is their path is going to curve like this. One's going to curve like that, and the other one's going to curve outwards like this. Okay, and they will have two different locations where they come out of this magnetic field. Let's say we have a detector over here, and that detector will then determine their positions. Well, let's calculate the radius of the path of both of these. So the radius of this first one would just be to here, right? And of course the other one would be a little bit farther out. So let's take a look at that. Okay, from what we know, the force magnetic is going to be acting like a force centripetal, because the path of these particles is going in a circle. So then we set the equation Q VB, and of course there's a sine of theta, but we are perpendicular, so the sine of 90 is equal to 1. That's going to equal mv squared divided by r being the radius of their path. Okay, and looking at this equation, then we can cross off one velocity there and remove the square there. And taking this to the left side and dividing, the radius then is going to equal mass times velocity divided by the charge and multiplied that by the magnetic field. And both of those are on the bottom. Okay, so that's going to be our equation to determine the radius of the curvature here. So let's go ahead and solve the radius of curvature for each of these particles. So the radius of the lighter one is going to equal 1.67 times 10 to the minus 27. We'll multiply that by the velocity of 1.00 times 10 to the 6th. And we'll divide this by the charge. Now these are hydrogen atoms, and one electron missing from that would be 1.6 times 10 to the minus 19. And then let's find the value of the magnetic field is 0.100. Now the radius then of protium, or the lighter atom there, is going to be equal to 0.104 meters. Okay, now looking at the second atom here, the heavier, we just notice again that the mass is twice the mass of the regular atom here, the protium. So we recognize that the radius would be then twice that, and so the radius is going to equal 0.204, or rather 0.208 meters. Okay, so that looks pretty good. Now, what about this? Now, we want to know the difference between the path lengths when they hit this side here. Now, we notice that the path length from here all the way to there is actually going to be 2r. So it enters here and curves all the way around there. When it hits the detector, that's going to be 2r, or simply the diameter of the circle. Okay, so what's the path length here for this particular atom? Well, I'll go double that. That's 0.208. And I'm just going to put a little circle around that. And of course, we'll need to double this one for the heavier atom. Okay, and that is 0.416 meters. So the lighter atom is going to hit in this direction here. It's going to go all the way around. That's going to be 0.208 meters there. The heavier atom going all the way here is going to be 0.416 meters from the point of entry. So if we want to get the difference between their path lengths, okay, we'll just subtract these two. And of course, if we look at that, the difference between the path lengths is going to be 0.208 meters. And I'll put a box around that. So what that means is the difference between here and this location is going to be 0.208 meters, and that's where the detector is going to see where these atoms come out of this mass spectrometer.